Hello friends, welcome to e-learning platform of Dr. Bapuji Sawanke Institute of Engineering and Technology's Mechanical Engineering Department. We started with our unit number 5, that is design of springs, and in this session we will continue with the same. So let's see what is Wahl's correction factor. So in previous session we have derived the equation for shear stress when the spring is subjected to some external load. So the resultant shear stress in the spring wire is given by tau is equal to Ks multiplied by 8 pd upon pi d cube. So this is the equation. In this equation we are using one factor, that is Ks, which is nothing but the shear stress correction factor, which is calculated by using the equation 1 plus 1 upon 2c. Okay, so this equation is used when the effect of curvature is not considered. In order, when a wire is bent in a form of helical coil, the curvature of wire increases the shear stress on the inner surface of the spring and decreases it on the outer surface of the spring. Due to the different magnitude of stresses induced on both the surfaces, there results in stress concentration at the inner surface. So in order to consider the effect of both shear as well as curvature of the wire, AM Wall derived the equation for the resultant stress, and this equation is given by tau is equal to Kw multiplied by 8 pd upon pi d cube, where this Kw is nothing but Wahl's correction factor, and which is given by the equation Kw is equal to 4c minus 1 upon 4c minus 4 plus 0.615 upon c, where c is spring index, which is the ratio of diameter, that is the mean diameter to the diameter of the wire. The Wahl's correction factor basically consists of two sub-factors such that Kw is equal to Ks multiplied by Kc, where Ks is equal to stress factor due to shear and Kc is equal to stress factor due to curvature. Okay, so when we have to consider the effect of curvature in the spring wire, we need to consider the Wahl's correction factor. Now the graph shows the relation between spring index and Wahl's factor. So here you can see the graph shows the effect of spring index on the Wahl's factor, in which Wahl's factor increases rapidly. So here the increase in the Wahl's factor rapidly as the spring index decreases. So this is all about Wahl's correction factor. Next is deflection in the spring. So figure shows the required schematic representation to calculate deflection in the spring. Let d is equal to mean diameter of the coil, n is equal to number of active coils. Therefore total active length of the wire, capital L, is equal to length of one coil multiplied by number of active turns. So here the L is calculated by using the equation L is equal to pi d multiplied by n. We know the torsion equation, which is given by T by J g theta by L. Then rearranging this equation for angle of deflection, then the theta will be TL upon Gj. Now put the values of the terms like T, G and T and J. So T is nothing but torque, which is calculated by using the equation, that is force multiplied by radius. So force is P and radius will be d by 2, and length is already calculated by using the equation pi d multiplied by n, upon g as it is, and j is nothing but pi by 32 d raised to 4. So after solving the equation, we will get theta is equal to 16p d square n upon j d raised to 4. Now the angular deflection of the spring is given by theta is equal to theta multiplied by length of the bracket. So the delta is calculated similar to the as we calculate the arc or arc length of the angle. So likewise here this delta is nothing but theta multiplied by d by 2. Substituting the values of theta, we get delta is equal to 8 pd cube n upon jd raised to 4. Therefore delta is equal to 8 pc square n pc cube n upon jd, where c is equal to capital D by small d. The next is energy stored in the spring. So figure shows the graphical representation between the deflection and the load acting on a spring wire. Consider a helical compression spring which is subjected to gradually applied load P, which causes the deflection delta. Within the elastic limit, the graph of load versus deflection will be a straight line as shown in figure. So the area below the load deflection line, so this total area gives the strain energy stored in the member. So it is similar to the right angle triangle. So the area of right angle triangle is calculated by using the equation half of base multiplied by width. So by comparing with area of right angle triangle, you will get the energy stored as half of, so the base is delta and the height will be p. So the equation will become half of p multiplied by delta. We know that the maximum shear stress induced in the spring wire, which we have already calculated by using the equation tau is equal to kw 8 pd upon pi d cube. Therefore equate this equation for p. So p becomes pi d cube tau upon 8 kw d. Then the deflection of the spring is given by the equation delta is equal to 8 pd cube n upon jd raised to 4. So put the value of force from this equation to this equation. So delta will be 8 pi d cube tau upon 8 kw d multiplied by d cube n upon jd raised to 4. So after solving the equation, you will get the delta as pi d square n tau upon kw gd. Then the total energy stored in the spring wire is calculated by using this equation, that is we have already calculated, that is half multiplied by p multiplied by delta. So put the values, you will get the equation u is equal to half of pi d cube tau upon 8 kwd multiplied by pi d square n tau upon kwjd. So solve this equation. So u is equal to 1 by 2 pi d cube tau upon 8 kwd, so pi d square n tau upon kwjd. So rearrange the equation. So you will get tau square upon kw square g multiplied by pi dn multiplied by pi by 4 d square. So here this pi dn is nothing but length and this pi by 4 d square is the area of cross section of the spring wire. So this area multiplied by length will become the volume. Therefore u is equal to tau square upon 4 kw square g multiplied by v, where v is volume of the spring. So this is the equation of energy stored in the spring. Springs in series. So when the springs are connected in series, then the total deflection by the springs is equal to the sum of the deflections of individual springs. So here the two springs are connected in series having deflections k1 and k2. So the total deflection delta is equal to deflection in this spring and deflection in this spring. So delta is equal to delta 1 plus delta 2. So from this figure we can calculate delta as P by K is equal to P by K1 plus P by K2, where K is combined stiffness of the spring. Springs in parallel. When the springs are connected in parallel, then the total deflection produced by the springs is same as the deflection of individual spring. So here delta is equal to delta 1 is equal to delta 2. As we know, P is equal to P1 plus P2, therefore delta K is equal to delta K1 plus delta K2, where this K is equal to, that is K is equal to K1 plus K2, where K is equal to combined stiffness of the spring. Okay, 2 minutes. Next is design procedure of spring. So first step is we have to find out the diameter of spring wire, that is the small d. So the diameter of spring wire can be calculated by using the equation of maximum shear stress, that is tau is nothing but tau is equal to kW multiplied by 8 pd upon pi d cube. So from this equation the diameter of the spring wire may be determined. Second step is mean diameter of the spring coil. So the mean diameter of the spring coil is calculated by using the equation of spring index, that is C is equal to capital D by small d. So by putting the value of D which we have calculated from above equation, put here and you can calculate the value of capital D, that is the mean diameter of the spring coil. Third step is number of turns. So generally the number of turns are calculated by using the equation of deflection, that is delta is equal to 8 pd cube n upon gd raised to 4. If the type of ends is not mentioned in the problem, then consider square and ground ends for the spring, and for that the total number of turns will be n plus 2. Next is solid length of the spring, which is calculated by using Ls is equal to Nt multiplied by D. Next is free length of the spring is nothing but Lf is equal to Ls plus delta max plus 0.15 delta max, and last is the pitch of the spring, that is small p is equal to Lf upon Nt minus 1. So this is the design procedure of the spring wire. So this is all about the springs. If you have any doubt regarding to this session, you can always contact me on this number. Thank you.